synchronous machine. Okay. So for our course, in this course actually we will only talk about the synchronous machine or synchronous generator. So swing equation means that we will actually derive the swing or the movement of the rotor of the synchronous generator with respect to some other parameters. Okay. So there will be some kind of mathematical equations in this slide. So we can move forward. The first step in analyzing power stability is to model the system components mathematically. So the first step is to model the system components mathematically. Okay. So let's say we are going to study the power system stability of a network, of the power system network. Okay. So actually the power system network that is actually present practically in the field. Okay. So we can clearly go there and we can actually put any fault or disturbance onto the line, and then we can actually observe the system, because it will make the system actually disturb, or it will actually make the system abnormal, right? So if we can do that, we can just put this fault or disturbance to any practical network of power system, right? So what can we do? Whether actually we can model the system by replacing all the components of power system networks like generators, transformers, transmission lines, loads, this type of things with their equivalent mathematical model. Okay. Then we can study that model, or we can simulate that model. Okay. Then we can intentionally put some faults or disturbances in that model, and we can study what is going on. Okay. And what will be the power stability of that system. Likewise, actually we can analyze the power stability of any power system network. That means that the first step is to model the system components mathematically. So there should be some kind of mathematical model. For our discussion, we will actually use this model. This is called the classical model. Okay. And this model is invented by these two scientists, Clipchamp and Freddy. Okay, so they actually jointly invented this classical model. So what is this model? This model is the simplest one, yet very useful representation of synchronous generator. Okay. So why simplest? Because obviously in this model we will exclude some practical phenomena, or we will actually exclude some complex scenarios or complex actions of the synchronous generator. Okay, so that's why it will be the simplest model, and at the same time it will be the useful representation. Why? Because it will be useful or helpful in understanding the basic phenomena of power stability. Okay. So actually for our convenience, we are making this model simplest, and at the same time it will be helpful for us in understanding the basic phenomena of power stability. Okay. And in this model, actually, the stability of a single generator connected to an infinite bus will be analyzed. So our system will be like this. That also we actually discussed in the first slide, right? This type of system is called single machine infinite bus system. Why? There is only one synchronous generator. That means there is only one machine, and there is only one infinite bus. What is infinite bus? Actually, this is representing the rest of our systems. There can be 99 or 49 more generators and associated transmission lines, transformers like this. Okay. So this system is called single machine infinite bus system, or shortly SMIE system. So in this classical model, we are going to analyze this system or this model, that is the single machine or single generator connected to the infinite bus. Now let's go to the disadvantages part. So as we have told earlier that this is the simplest model. So obviously we have to do some sacrifices, right? So we will include some complex scenarios or some complex actions of synchronous generator, right? Okay. So what are they actually? Actually, this classical model is not appropriate for generators with fast acting exciters, then governors, and power system stabilizers. Okay. So let's talk about these two things, that is the fast acting exciter and the governor. Okay. So what is the exciter system in terms of the synchronous generator? Can anyone say what is the transform exciter system? Yeah. Yeah, it is actually the DC supply, right? The DC bias to the actually the rotor winding of the synchronous generator. Okay, that will be the exciter. And what is the governor? Can anyone say? Actually, governor means to provide some kind of control in the prime mover side. Okay, prime mover on the turbine side. Okay, so if I draw the this system combining the governor and the exciter, then it will actually look like this. Let's say this is our generator, right? So inside the generator, obviously there is rotor, right? Let's say this is our rotor. There are two poles, pole 1, pole 2. Okay. So first we have to rotate this rotor somehow, right? Using prime mover, right? So let's say this rotor is connected to my external prime mover. Okay. So this is our prime mover. Prime mover is nothing but the turbines. Okay. The turbine. We are giving some kind of mechanical input in this side. Okay. And that mechanical input actually is rotating this rotor. Let's say we are giving some kind of mechanical torque or some twisting force in the input side, and with this torque we are actually rotating this. Okay, we are rotating this rotor. This is the rotor. Now, how can we convert this actually mechanical energy into the electrical energy? For that purpose, actually we have to give some kind of DC excitation here. Okay, so let's say this rotor will be connected to one DC circuit. This is our external DC circuit. Let's say as the voltage source is VDC. Okay. So for this voltage source, there will be some kind of current flow across this rotor winding. Okay. So this prime mover is rotating the rotor. Okay. And there are some kind of current here. So combinedly, these two will create rotating magnetic field. Okay. Actually, which will induce some kind of voltage in the stator winding. Okay. And that voltage will be converted as the electrical energy or electrical output at the output side of this generator. Okay, so that is actually the basic principle. So this is actually the exciter, and there if we have some kind of mechanism to actually control this prime mover or actually to control this rotation, okay, that system is called the governor system. Using this system, we can actually control the flow of fuel, okay, and actually subsequently we can control the movement or the speed, okay, at which this rotor is rotating. Okay, so this is the governor system. So using this governor system, we can vary the speed or the rotation of this rotor. So there are two things: exciter and the governor. So we are neglecting the fast acting exciters, that is the dynamics of the exciter. Okay, so we are neglecting the dynamics of this exciter. Okay, so we are neglecting this. What is the meaning of that? That means that this will be a fixed voltage. Okay, we can vary this voltage, and actually the current supplied to this rotor winding will also be fixed because there is no dynamics associated with this exciter system. Okay. So this assumption means that we will have a fixed amount of current in the rotor winding. Okay, and also we are not considering the governor system. That means that we have no control over the prime mover or over the speed of the rotor actually. Okay, so the prime mover is rotating the rotor. So we are neglecting this governor system. That means we do not have any control over this prime mover. Okay. So it will actually rotate at some kind of constant speed. Okay, so that is actually the case without the governor system. this thing we will also see in the next slide. That this will be our assumptions. So based on these disadvantages or based on these cases, we will see the next slide. Okay. So here we have three disadvantages that are actually this model, this classical model is not appropriate for generators with fast exciting exciter, governors, and power system stabilizers. Okay. So in this model, in this classical model, we will not consider the dynamics of our exciter systems. Okay. Also, we will not consider any kind of governor system, as well as we will not consider any power system stabilizers. Okay. So what is actually power system stabilizers? Actually, this is one kind of additional control scheme. Okay. So whenever the system goes to any unstable state following a disturbance or a fault, at that time this power system stabilizers actually work as the control system, or actually it tries to again convert that system to the stable state. Okay, so that is the task of this power system stabilizer. But in this course, in this power system 3 course, we will not actually discuss or we will not study this power system stabilizer. Okay, because this is one kind of advanced topics. Because this is a very big circuit. Okay, actually that circuit actually is responsible to convert any unstable system again to the stable one. Okay, that is the task of the power system stabilizers. But we are considering that in this classical model there is no power system stabilizer. Okay. Then what is the advantage? Obviously, we have neglected some of the complex actions of the synchronous generator. That's why this model is the simplest one, right? As well as this model is the mostly used model in the domain of swing equation. Okay. So the advantage is that if we somehow can understand this model, then it will be sufficient for us in understanding the basic phenomena of power system study. Okay. So in that essence, this classical model is actually advantageous for us. So any questions from this slide? Any question?
Sir, when we are saying model, ASM IB model that is a classical model.
Actually, here the model is the classical model. Okay, and for this model, we will actually use this system. This is the simple machine infinite bus system. Okay, so this is the network. Okay, and actually the network that we have derived here. Okay, this network is derived here considering the classical model. Okay. So now in the next slide, so these are some assumptions for classical model. Actually, we have discussed some of the disadvantages here. So based on these disadvantages, these assumptions can be drawn. The first point, the exciter dynamics are not considered. Okay, so that's why the field current is assumed to be constant, so that the generator stator induced voltage is always constant. Okay, so here you can see that the exciter dynamics are not considered. That's why there are two terms, field currents and the generator stator induced voltage. Okay, so these two will be fixed. We have already discussed here that if we do not consider any dynamics in the exciter system, then the current flowing to this rotor winding will be same, right? So our field current IF will be same. So if the field current remains same, our flux also remains same. Okay, and then the generator induced voltage. Okay, there is some formula for this EG, or the generator stator induced voltage. Okay, it will be like KG multiplied by phi. Okay, multiplied by the synchronous system. Okay, this is the formula. So this is one kind of machine constant. Okay, it will vary machine to machine. Okay, so let's say it will be dependent on the number of poles or number of parallel paths like this. Okay, so this will be kind of one kind of constant. Then this is the phi. Okay, so here we have assumed that our IF is constant. That means our phi will also be constant. Okay, so here this term will also be constant. What is the NS? NS is the synchronous speed of the synchronous generator. You know that this is a fixed speed, right? The formula of NS is equals to 128 over P, right? So 8 is our operating frequency, P is the number of poles of the synchronous machine. If we apply this formula, then also this NS will be a fixed value, right? So in this formula, all of these parameters are fixed. Okay. So our EG will be constant as well, right? Actually, EG will change according to the final, but here the final is constant due to the fixed IF value. Okay. As we are not considering the dynamics of the exciter system. So that's why our field current IF as well as the generator induced EMF or generator induced voltage EG will be constant. Okay. So this will be our assumption number 1. Then the effect of damper windings present on the rotor of the synchronous generators is neglected. Okay. So in the later part of this slide, we will actually study the damper windings. Okay. So in that portion, we will learn it actually elaborately. Okay. But for the time being, consider this damper windings as some kind of protective equipment, okay, or the protective elements. Why? Because whenever our system goes to unstable state due to some kind of fault or disturbance, okay, let's say this is our delta of the rotor angle, this is the time, okay. So let's say in the initial moment, delta is not changing with respect to time, okay. So this is a fixed value. That means our system is now at a steady state condition. Then there is some kind of disturbance or fault in the system. That's why the system is now going to the unstable state. Okay. So unstable state means this variable will be now changing with respect to time. So let's say this is not changing. Okay. There is some kind of swing in this delta term. Okay. Now if there is some kind of damper winding present on the rotor coil, task of these damper windings are to actually is to die out these oscillations. Okay. So if we have damper windings in the rotor coil, so it will actually die out these oscillations, and then again the system will go to the steady state. But actually this delta will again it will reach to a fixed value. Okay. So this die out or the damping effect, this is called the damping effect. The die out oscillations. Okay, so this damping effect is due to this damper windings. Okay, and after that, after a few moments, again our delta will be a fixed value, or our system will reach to the steady state condition, right? The windings means some kind of coils. Okay, so we will discuss this thing in the later part of this slide. Okay, there will be some kind of figures, some kind of mathematical expressions for this damper windings. Okay, but for the time being, just know the task of this damper windings. And if damper windings are present in the rotor, that means if there is any kind of fault, if the delta value actually starts to swing, so after some moment it will again reach to the steady state value. Okay, with these damper windings, because these damper windings will die out the oscillations in the delta due to the disturbance. Okay, so this effect is called the damping effect, and the circuit that is responsible for this task is called the damper windings. Okay, so we will elaborately learn this topic in the later part of this slide. After 19, just know this thing about the damper windings. Okay, we will again come to this point. Then the third point is that the input mechanical power, that is the PM. PM is the input mechanical power. Okay, this is the PM, input mechanical power to the generator is assumed to be constant. Okay, so it is also assumed to be constant during the period of the experiment. Why? Because look at the previous slide, we haven't considered the governor system, right? So governor means to give some kind of control in the prime mover side, with the input side. So if we do not have any control in the input side, so actually our input will always be same. That means we can actually change the speed of this rotor. That means we can actually change the amount of mechanical input in in the input side because we do not have the governor system. Okay. If we have the governor system, then we can change this input value. Okay. That's why it is assumed that the input mechanical power PM to the generator side is assumed to be constant during the period of operation. Then the last point is that the saliency of the generator is neglected. Okay. Based on the saliency, there are two types of synchronous machine, right? One is salient core machine and another is non-salient core machine. Can anyone explain these two types? What is actually salient core and what is actually the non-salient core? Anyone? What is the saliency? Which type of rotor is this? Can anyone say? Is it salient core rotor or the non-salient core rotor? This is. What is the meaning of salient? Salient means actually the countable. Okay. So if we count the number of poles by looking at the rotor construction, then we will call that rotor as the salient pole. Okay. And if we are unable to count the rotor pole numbers, okay, then we will call that one as non-salient. Okay. So let's say we can easily count the pole number here. This is one pole, this is another pole. Okay. So this is actually two pole machine. Okay. So actually this is the salient pole rotor, and here the number of poles is actually 2. Okay. Now if you want to draw the 4-pole salient machine, okay, the picture will look like this. Okay, so look, you can actually count the pole numbers, right? 1, 2, 3, 4. This is the 4-pole machine. The type of the rotor is salient pole rotor. Okay. Then what is actually the non-salient pole rotor? Actually it is the cylindrical one. Okay. So let's say this is the cylindrical type of rotor. Cylindrical type of rotor. Okay. And in this construction, there are some rotor coils inside. Okay. So this is the cross-section view of the cylindrical type rotor. Actually, by looking at this rotor, we can actually count the pole numbers. Okay. So that's why this type of rotor is called the non-salient pole rotor. Okay. This is the non-salient pole rotor. So actually, yeah, in this classical model, we will neglect the saliency of the generator. That means we will not study about the salient pole rotor. Later our discussion will be on the non-salient pole rotor. That is the cylindrical type. Okay. So that is the generator is assumed to be of cylindrical type. So we will not actually consider the saliency of the generator. Okay. So we will not study about the salient pole rotor. Rather we will study about the non-salient pole rotor or the cylindrical type. Okay. So now yeah, actually there are the rotor windings are mounted in such a way that actually by looking at the rotor you can count the exact pole number. Okay. So that's why this type of rotor is called the non-salient pole rotor. Okay. The rotor poles are actually not salient here in this type of rotor. And in our classical model, we will study this type of rotor and we will neglect the saliency of the rotor. Why? There is one certain reason, that is we will study this thing, okay, because in the later part of this slide there are the difference between the salient pole rotor and the non-salient pole rotor. Okay. At that part we will see that there are some complexity in case of this non-salient pole rotor, because look, this rotor is rotating, right? So let's say this is the rotor, okay, and outside this rotor, this is our stator, right? Of the synchronous generator, stator. So in the stator, we coil A, coil B, and coil C. Okay. So whenever this rotor will rotate, so this is the pole, right? So in this moment, this pole is here. So the distance from this pole, okay, to A and C is now like this. Okay. But whenever it will come to this place, okay, there are some air gaps. Okay, so these are the air gaps actually. Okay. And this is not actually the uniform one like this. Okay, so if we just round this shape, then it will be the non-cylindrical rotor. Okay, so if this is the round one, then whenever this rotor is rotating, for all the time, the distance from this coil will be same. Okay, so and from this distance we can calculate the reactance. Okay, so at this time the reactances will be same for the non-cylindrical rotor, but for the cylindrical rotor, as there are some air gaps, so the distance will always change. Okay, so depending on the changes in the distances, the reactances will also change. Okay, so we will study this type of thing at the later part of the slide. Okay, so that means that in summary, actually for the non-cylindrical rotor, the reactances are not actually same. Okay, there are two types of reactance. Okay, so we will study this thing. Okay, no problem. There are two types of reactance. One is called G-axis reactance and another is the Q-axis reactance. Okay, so these two reactances are different for the cylindrical rotor, but for non-cylindrical rotor, these two reactances are actually same. Okay, that's why for removing the complexity in our system, we are negating the salience of the generator, and we will only study the non-cylindrical rotors. Okay. Now, what is the advantage? So this previous assumptions, okay, so these four assumptions actually will make the representation of synchronous generator easy for us. Okay. So do you have any question in this slide? So these 4 points actually are the assumptions for our classical model. Okay. That we will now study to derive our swing relation. Okay. Any question? Do you have any question in this progress? To become it as cylindrical and non-cylindrical. Okay, actually for the cylindrical, actually the pole numbers are normally even, like 2, 4, 8, 16. Likewise, you can increase the pole number, right? Okay, but at certain point, if the pole numbers are actually higher, then again it will not be able for us to detect the number of pole numbers, right? Then the rotor type can be shifted to the non-cylindrical rotor. But actually, I do not know any kind of limitation with the pole numbers. Okay, but if we increase the pole numbers like 32, 64, 128, okay, so at some moment actually it will be shifted to the non-cylindrical rotor. Okay. Any questions in this two slide? Because if you understand this two slide properly, then our rest of the discussions will be very much easier for us. Okay. So I think these two slides actually seem a bit difficult to you, right? To compare to your previous slide that we discussed in the last two classes. Because actually here we have discussed a lot of things. Because look here, this temporal units we will learn it separately. Okay. Also this saliency, okay, we will learn it separately in the later part of the slide. Okay. The only thing you have to understand for now is that these two systems, exciter system and the governor system. I think you have understood from this figure, right? What is exciter and what is the prime mover. And if you have also understood that if the dynamics of the exciter is not considered, then the field current will be constant as well as the EG or the generator induced EMF will be constant, right? This portion you have understood, right? Also, this governor is the control over the prime mover. So if we have the control over the prime mover, then we can change the input torque, okay, to the generator input side. But if you do not have the governor system, then you do not have any control. That means your mechanical energy input PM will always be constant. Okay. So actually from this part we are actually making this assumption as we do not consider any governor system in our classical model. That's why the input mechanical power TF will be assumed as constant, okay, during the study of our analysis. And this power system stabilizer, actually this is a advanced topic. Actually, just for the time being, remember that actually this system is actually one kind of additional control system. Okay, so whenever the system goes to the unstable state due to some disturbance or fault, actually this circuit tries to convert that unstable system again to the stable one. Okay, so this is the task of this kind power system stabilizer. Then here actually the assumptions, these assumptions 1 and 3 from the exciter point of view and the governor point of view. Okay, and here this thing we have just neglected the damper windings. Okay, so and in the later part of the slide we will also study the effect of the damper windings. Okay, at that time it will be clear to you that what will be the complexity related to this damper windings. Okay, if we include this in our model. Then this point is the saliency. Okay, we have just neglected the saliency. Okay, so whenever we will discuss about the salient code and the non-salient code in the later part of the slide, at that time we will understand that actually how the HG or the T-axis reactance and the SQ or the Q-axis reactance actually changes in value for the salient code machine. Okay, and for the non-salient code case, these two are actually equal. Okay, which will make our calculation easier. That's why we are considering the non-salient code machine. Okay, because classical model is the simplest model. Okay, so here we will actually ignore any kind of complexity. Then the advantage is that these assumptions make the representation of synchronous generator easy for us. Okay. Any other question? No, right? Now we can go to the next slide. So this is our example system, that is the single machine infinite bus system. Okay. So I think I have already discussed this system in our first slide, right? So now I will ask some questions and I want some answers from you, right? Can you now say what is this? This is a pass bus, right? Okay. Then what is this? Transformer, right? What is the task of the transformer in this circuit? Equation of the voltage, right? So in this side there will be kind of low amount of voltage. So in this system of transformer we will convert this low voltage to the high voltage in this side. Okay. Then this synchronous generator, right? Of the alternator. Then these two are the transmission lines. Okay. So there are two transmission lines parallel to each other. So this type of transmission lines are called double circuit line. Okay. So double circuit transmission lines. And this is actually the infinite bus, right? This is the infinite bus. Okay. So the voltage magnitude and the frequency actually remain constant in the infinite bus, right? I have already discussed this thing in the last class maybe. Okay. And another thing is that I have discussed that in our calculation actually we will take this infinite bus as our reference. Okay. And can you remember that part? That whenever we will calculate the parameters like this delta or this E prime, this type of things, okay, we will first take this infinite bus as our reference, okay, because here the voltage magnitude and the frequency remain constant. So that's why whenever we take any system as our reference, we set that angle at 0 degree, right? And with this 0 degree, we will draw the other phasors, right? Like let's say in the later part of the slide, we will see that we will draw some kind of phasor diagram, okay? And in that phasor diagram, first we will draw this thing, right? Because this is our reference. So we will draw like this. It will be the like this, okay? So this is our V angle 0. Why 0? Because this is the horizontal one, right? So here the angle is 0 degree, okay? And considering this as our reference, we will draw the other phasors, okay? So we will see this thing in the later part of the slide. Okay, but for the time being, just remember that this is our reference. This is infinite path. Okay. Then can you now say that what are these rectangular boxes? Yeah, exactly. These are the actually circuit breakers. Okay. Protective equipments of this circuit. Okay. Now I think all of the things in this diagram should be clear to you, except these two. Okay. So this and this. Okay. So this is our voltage magnitude for the synchronous generator, and this is the angle associated with this voltage. Okay. Actually, this delta is our rotor angle. Okay. And in the last class, we studied different types of stability, right? And I told you that we will only study the rotor angle stability, right? So here our main focus is this parameter. Okay. So whenever our system will go to the unstable state, this delta will actually vary. Okay. This delta will be our main parameter that will be varying with respect to time in the unstable state. Okay. And then in the stable state again it will be fixed with respect to time. Okay. And this is the voltage magnitude, and this is the reactance. Okay. X means the reactance. And what is this G? This G is for the direct axis. Okay. For the D axis in short form. Actually, this thing will be discussed elaboratively in the later part of this slide. Okay. We will learn about the XG and the XQ. Okay. This is the Q axis or the quadrature axis, and this is the direct axis. Okay, or the XG. Okay. So just for the time being, know that this D represents the D axis or the direct axis. Okay. And X is the reactance. Okay. Now there is one important thing is this dash. Okay. Can anyone say that what is the meaning of this dash here? Which kind of quantity actually is it representing? This for this dash. This dash. Yeah. For actually this is representing the transient quantity. Transient. Okay. I think in any of the power system or machine courses you have learned this type of things that wherever your system goes to the unstable state, okay, there are three regions. Okay. In the first few cycles there will be the sub-transient region. The sub-transient region. Okay. And all the parameters here will be represented by kind of double dash. Okay, like this. Let's say XQ double dash, E double dash. Okay. This is the sub-transient region, and the period of this region will be, let's say, from 0 up to 2 complete cycle. Okay. And this amount is very much less. Okay. Then the transient state. Okay. So this is the transient region. Actually, it will be from 2 cycles to, let's say, 20 cycles. Okay. This time will be for the transient region. After that, whenever we will have to eliminate all the instability associated with our system, then our system go to the steady state region, right? So this is the steady state. This is after 20 seconds. Okay. So can you remember this thing? This 3 step? Can you actually have you ever seen this type of diagram? Like in the first few cycles there will be lots of variations, right? Then maybe the next few cycles the variation will be less. Then again we will go to the steady state, right? So this first few cycles will be in the sub-transient state, it will be the transient state, and then finally it will be in the steady state. Okay. So this is in terms of the cycle, the complete cycle. If we want to think it as a time frame, okay, so one cycle means the frequency is 50 Hz, so one cycle means 20 milliseconds, right? 1 over f 1 divided by 50 will be 20 milliseconds. Okay, that means from 0 to 40 milliseconds our system will be in the sub-transient state. And from 40 millisecond to 400 millisecond, okay, it will be in the transient state. Then after 400 millisecond, it will be in the steady state condition like this. Okay. So here actually our study will be in this state. Okay, transient state. Okay. So here we are discussing about the local angle stability, and actually this event can be clearly understood in this transient state. Okay, so that's why we will only consider all our parameters as the transient parameters, because this state is very much small. Okay, it actually dies out with a few amount of time. Let's say from 0 to 40 millisecond. After 40 millisecond, it actually completely dies out. This sub-transient state. Then it goes to the transient state. Okay. So in the transient state, it actually remains comparatively larger amount of time. Okay. So that's why we will study in this video. That's why all our parameters here, this E and the X or the reactance, reactance, these are actually the transient parameter. Okay. And to represent the transient parameters, we actually simply put one dash in the as the superscript of our in the parameter. Okay, in the parameter. Yeah, in the steady state, all our parameters will be like E, then XD, X cube like this. Okay, with no dashes. Okay. So for subsequent subtransient, double dash. For transient state, this single dash. Okay, like this. For steady state, there will be two dash. Okay. Then this actually are this is the transformer reactance, and this two are the line reactances. Okay. Have you understood up to this? Any confusion in this place? Now, with this diagram, we can easily draw the equivalent circuit model, right? Like this. Can we draw this? We have one synchronous generator here. Okay, so this is represented by this circle, and here the voltage is P prime, and the associated proton angle is delta, right? Then we have transient G-axis reactance for the generator. Okay, so that is here. Then transformer. So for transformer, there is only transformer reactance. Then we have two transmission lines, line 1 and line 2, and these two lines have XL1 and XL2. These two transmission line reactances. Okay. Then finally, this system is connected to the infinite bus. Okay. So this is our infinite bus. So that the voltage magnitude is V, and the angle will be 0 degree, right? Then, is there any other question of our circuit? No, right? Then we can simply connect this to in the ground. Okay, let's see this is our ground. So like this, we have just taken these two, and we are actually making this two as short circuit, and this is our, let's say, ground connection. Okay. Any other confusion here? Have you understood how actually we can draw this equivalent circuit representation for the SMIB system from the figure diagram? I think it should be clear to you, right? Okay. Now there are some assumptions here. Okay, look. The first assumption is that there are only reactances of the synchronous generator, then transformer and transmission line are considered. Okay. So here we have only considered the reactances. Okay. So we haven't considered any resistances, right? So only we have considered the reactances. Okay. This is the assumption. Okay. There is no reason behind it. Okay. But for this assumption, there will be only reactive power loss due to these reactances. Okay. But as there are no resistances, there will be no real power loss, right? Because our real power loss is associated with the resistances, and actually the reactive power loss is actually associated with the reactances. Okay. So if there is no real power loss, so whatever real power is supplying from this side, the same amount of real power will be delivered to this side, right? Without any real power loss. Okay. So that will be our assumption. Then these three assumptions, I think you should know this thing. Okay. The infinite bus represents rest of the system or grid where the voltage, magnitude and frequency are very constant. We have already discussed this thing. Then the infinite bus can act like infinite source or sink. That means that whatever power you take from this infinite bus, okay, it will not make any difference. Okay, or whatever power you are actually supplying to this infinite bus, it will not actually make any difference, right? So that means it will be acted as infinite source or infinite sink. Okay, are you familiar with this two terms, source and sink? Okay. Now we can actually say that this infinite bus is acting as the infinite source or infinite sink, right? Then it can also be considered as a generator with infinite inertia and fixed voltage. Okay. As this actually this infinite bus is representing the rest of the generators like 49 or 99 generators of our system. So we can think it as a big generator, okay, with infinite moment of inertia and actually the fixed voltage. Okay. So I think we already know this thing about the infinite bus. Okay. Now with these assumptions we can go forward. Okay. Now our task is to study the mechanical model of the generator. Okay. We will also study the electrical model, but first we have to derive some kind of formulas from the mechanical model of the generator. Okay. So this is the mechanical model of the generator. Okay. So let's say this is the moving part of the generator, that is the rotor. Okay. This is the moving rotor. The rotating body of the generator, that is the rotor. And this is the J. What is J? J is the mass of inertia, right? So in the linear motion, we know that m is the mass. But for the angular motion, this m is equivalent as this J, or the moment of inertia, right? Now this is our input side, and this is the output side. Okay. Now in the input side, we are giving some kind of mechanical input as this mechanical torque. Okay. Torque means the twisting force. Okay. So we are twisting this side in this direction. Okay. This is the direction of the input torque. Okay. That is the TM of the mechanical torque. Due to this torque, there will be some kind of movement in the rotor, right? Obviously, there will be some kind of movement. So, what will be the speed of that movement? This direction should be aligned with this direction, right? With this direction of the given torque. So, this input torque and the speed of the movement of the rotor should be aligned in direction, right? So, these two directions will be same. Now, according to the Newton's third law of motion, we know that every action has its equal and opposite reaction, right? So, due to this kind of action on the input, at the output side, we will see some kind of reaction, but in the opposite manner, right? So, this is our reaction, or this is our output in the output side. That is our electrical torque. Okay, as this is the generator, so with some kind of mechanisms, it will convert this mechanical torque into the electrical torque. Okay, so this kind of energy conversion is called as electromechanical energy conversion. Okay, so we are actually converting our mechanical energy to the electrical energy. So what will be the direction of this torque? It will be opposite to this input torque. Okay, everyone understand this thing? So this is very much important. Okay, so the actually in the example maybe it will be asked to you that define the direction of the Tm, omega m and the T. Okay, then you should write that or Tm and omega m, or the angular speed in the input side of the rotor should be aligned with each other, but the electrical torque or the T will be in the opposite direction. Okay, everyone understand this thing? Yeah. Yeah, actually this is the we can actually explain this thing using two formulas like Lenz's law. Okay. Lenz's law. What Lenz's law actually says, the effect and the causes actually will be in the reverse direction, right? So this is our effect, and what is the cause? Cause is the mechanical force. So this should be in the opposite direction, right? Also, Newton's third law of motion says that every action has its equal and opposite reaction, right? So if this is the action and if this is the reaction, so this reaction should be in opposite manner of this action, right? So that's why these two directions will be in the opposite side. Okay.
So Newton's third law, the reaction is active at the last one law, which causes the action.
Yeah.
So the body in the first one, so the reaction will be active on the EM or so, which is the rotating axis on the generator side.
So you are saying that, sir, this should be your reaction, right? Omega n. This omega n is actually the by default term due to this Tm, because whenever there is some kind of mechanical force on the input side, there should be some kind of movement, right? And this movement should be aligned with this Tm. So this should be our basic understanding, right? So if this is a ball, if we just apply a force in this direction, so movement will be obvious in this direction, right? Not in the opposite direction, right? এখানে তো আমাদের there are lots of mechanisms inside it, right? But we are just saying it as normal that this is our react. This is actually our the byproduct, or actually the reaction, because this is our final product from this thing, right? So in the first time we are giving some kind of mechanical torque, and at last we are getting the electrical energy. This is our last term, right? And in the middle there are lots of mechanisms here inside it, like prime mover, then rotating magnetic field, exciter system, this type of things. But our final byproduct is this thing. So we can refer it as the reaction with respect to this action. Okay. So in this figure we can say that this T will be in the opposite direction of this Tm. Okay. Okay. So now from this diagram or for this moving body, we can write the dynamics equation. Okay. And this equation will be represented by this. Okay. Actually, this is the Newton's second law of motion, which says that m equals to ma. Okay. And for angular motion, actually torque is our f, right? For linear motion, this is f, but for the angular motion, this twisting force is represented by the torque, right? So there are two torques, Tm and Te, but both are in the opposite direction. That's why we have to take the net amount of torque. Okay, that will be Tm minus T. That will be our net torque. Okay, it will be equal to some kind of Ma, right? So what is M here for the moving body? Yeah. Question? Here, what will be our M? M will be here the J, right? Yeah, for the actually angular motion, our actually moment of inertia is equivalent to the mass of the linear motion, right? So this is actually J, right? Here for the linear motion it is actually M, okay? And then the acceleration part, okay? So this is the acceleration part. Okay. How can we find the acceleration? By the double derivative of the distance, right? So here this theta m is the distance of rotor, okay? So this is the rotor position, theta m. Okay. So if we do the first derivative, then we will get the omega n or the angular speed, okay? Then if we do the second derivative or the double derivative, then we will get the angular acceleration, right? So this is actually equivalent to the acceleration term, okay? So this equation is nothing but our Newton's second law of motion, right? That is F equals to ma. Can we get this two? Do you have any confusion here? No, right? Now from this slide, actually, I think today we have no time. So actually, I intended to cover a few slides more. Okay. So my target was to cover up to this slide. Okay. This slide. So but actually, somehow actually we ended up with this slide. Okay. So I think in the next class we can start from this slide. But now if I give a recap for you, actually as this is kind of power system course, and whatever my experience is that actually the students actually do not actually get any interest in this power system course, right? So that's why I am trying to make every lines or every slide easier for you, okay? So that I want to make sure that you all are realizing all the lines and all the places, okay? That's why if you have any confusion, you can ask during the class or all of the class. But just make sure that you understand all the topics. So in today's